um, my labs that I had said that I would change some due dates and hadn't. And so I went through and did that this morning. Did anybody want to look at any of the exponent homework? I would ask if anybody wanted to go over the test, but I want to just hold off one more day in order to do that. Did anybody look at that homework 19 and have any questions on it? Did you guys want to go over some of those problems before we begin today or no?
I did it, and then I think I got like 2 or 3 wrong, and then I just redid those, and I just watched the video and watched it twice, and it was.
So you got it.
Yeah.
Okay. Are you watching the videos in my labs?
I did.
Okay.
I did watch the other one on the negative exponents, but I had already, I think it was maybe within a day or two of watching the other one. And it was just kind of was like I was getting cross-eyed from saying the same thing. And
okay,
but it wasn't,
All right. Does anybody else want to look at any of the others, or should we just start picking up from where we left off? Not hearing from any of you. I guess we'll pick up from where we left off. We've been looking at exponents and polynomials, and let me just real quick make sure that I have the chat open in case anybody wants to talk that way. And again, just that homework 19 was really the only one that I feel like we've kind of covered sufficiently to be due today. The homework 20, 21, and 22 will be due hopefully Thursday, but let's see if we get through. I think 22 deals with the addition of polynomials. 20 works with the negative exponents, and 21, now I'm having a brain fart. Give me a minute. I believe that 21 works with the scientific notation. Let me just make sure. No, it works with polynomial definitions. 22 works with the negative exponents and scientific notation. And while we had looked at negative exponents, we had not yet looked at the idea of scientific notation. So let's do a quick review of what we've got so far in terms of exponent laws. We had said that if we have the same base and we're multiplying two factors that have the same base with an exponent, in order to take the product, we said we'd add the exponents. We then said that if we have the quotient, and I have to apologize, I'm looking and we did not get as far as we thought. So I'm going to take this one and also move it back to the 22nd. If anybody's completed that already, I'll give you extra credit if it's done already. And I apologize for that. I had thought we had gotten further. Then we said that if we have same base and we take the quotient, we take the difference of the exponents. That law gave us the possibility of a zero exponent. And we said that anything to the 0 power is 1. That law also gave us the possibility of a negative exponent. And we had said that a negative exponent means take the reciprocal. And if I remember, that was where we had left off. So looking at an example, let's say, for example, I have x to the 4th times x to the negative 3rd. Here, because I have the same base and I'm multiplying, I'll add those exponents. and that will give me x to the first. Instead, let's say I have y to the third over y to the negative third. Here, because I'm dividing, I'll subtract the exponents. And being careful with the signs, subtracting a negative is like adding a positive, and that'll give me y to the sixth. Let's say another example. I have 2x y to the negative third over 4z to the negative first. And usually with these, you're asked to express with positive exponents. And we had said last class that because that negative exponent means 1 over, it means take the reciprocal. And so over here, if I have a negative exponent in the, well, I'm talking too soon. Anything that has a positive exponent, which will be my 2, my x, and my 4, will stay where they are. Anything that has a negative exponent in the numerator, the exponent will become positive when I move that factor to the denominator.
Would it be wrong to simplify the 2 and the 4?
You know what? I'm just going to do that last step, but if
Okay.
you want to do that beforehand, great. Thank you for noticing that. And if I have a negative exponent in the denominator, it will become positive in the numerator. And then, yes, we do need to reduce that fraction. 2 over 4 would be 1/2. And so I would have 1xz over 2y to the third as my final answer. You can put the 1 in there saying 2 over 4 is 1/2. But again, there's no need to show multiplication by 1. Another example, let's say I have x to the third, y to the negative second, over x to the fifth, y to the fourth. When I look at this, I first see it as a division problem. So in order to divide on that common base, I'll subtract the exponents. On x, it's always the exponent of the numerator minus the exponent of the denominator. And on y, it will be the exponent of y on the numerator minus that in the denominator. So simplifying, that gives me x to the negative second, y to the negative sixth. I can think of them as being over 1 because they have a negative exponent. That means I want to move both of those to the denominator to make that exponent positive, which will give me 1 over x to the second, y to the sixth. How does that one look to everybody?
Just a quick question on the one above with the negative exponent going into the numerator.
Mhm.
Could you just explain that really quickly?
Okay, I'm going to just look at, real quick, let's look at something, just let's say 1 over z to the negative first. If I look at that, that means 1 over z to the negative first by definition is 1 over z, but we don't want to leave a complex fraction. And so I can think of that as the numerator divided by the denominator. And when I divide fractions, I keep the first, change the division to multiplication, and take the reciprocal of the second. To divide fractions, you multiply by the reciprocal, that idea of keep, change, flip. And so that multiplying just gives me z over 1. And if you want to do that, work every time you can, but instead, let's say I have 3 x over z to the negative third. I can say that if I have a negative exponent in the denominator of the fraction, that exponent will become positive whenever I take the reciprocal, whenever I move it from the denominator to the numerator. Likewise, if I have, let's say, 3x to the negative second over z, if I have a negative exponent in the numerator, that exponent on that factor will become positive when I move it to the denominator. So that if I have a negative exponent on a factor in a fraction, if I move it to the other part of the fraction, that exponent can become positive. So a factor with a negative exponent in the denominator will have a positive exponent in the numerator, and a factor with a negative exponent in the numerator will have a positive exponent in the denominator. Does that make sense?
Yeah, but is it wrong then if we just automatically switch them, or do we?
No, that's, you can automatically switch them. You don't
Okay.
need to do the work. So, for example, if I have 3x to the negative fifth, that 3 has an exponent positive 1. I'm going to rewrite it showing that. Usually you don't take the time to rewrite it. But because that 3 doesn't have an exponent, it has an exponent of positive 1. So it will stay positive in the numerator. That x has an exponent of negative 5. And so it will become a positive 5 when I move that into the denominator. Better?
Yep.
Then the next rule, and I apologize, I thought we had completed these, I'm ever so sorry, is the power rule. And with the power rule, it's what happens when you raise a power to a power. And so let's look at an example first. Let's look at something like x to the second to the third. Well, when I raise something to the third power, I multiply it by itself 3 times. And each of those x squareds means I'm multiplying 2 x's. And so looking at it drawn out, does it make sense that there I'm multiplying a total of 6 x's and I get x to the 6th? And if you're a glutton for punishment and you want to do as much work as possible, you can draw them out each time. But instead, I think it's easier to notice that in order to get that x to the 6th, I would multiply those exponents. And so if I have x to the m to the n power, that gives me x to the m times n, or when I raise a power to a power, I multiply the exponents. And I'm just thinking as I'm dragging down that I'm making this page awfully long. And so I'm going to give you guys a second to write that and then turn the page to look at some more examples. Is everybody ready?
Yep.
So first example, if I have y to the third to the fifth, that would give me y to the 3 times 5, or y to the 15th. And again, when you're doing them on your own, it's not necessary to write that middle step. I'm just writing it out for all to see. So what if I have x to the negative third to the fourth? When I multiply negative 3 by 4, what do I get? Three times 4 is 12. Positive times negative is negative 12. And now because that's a negative exponent, and the directions will ask you to express everything with positive exponents, I need to make a fraction, and that exponent will become positive when it moves to the denominator. If there's nothing in the numerator, we'll put that 1. Another example, let's say I have z to the negative third to the negative 7. When I raise a power to a power, I multiply those exponents. So I'm thinking negative 3 times negative 7. Well, 3 times 7 is 21, and negative times negative is positive. And so that has a positive exponent, and we can stop there.
Just a quick question. How come with the x minus 3 to the fourth, you move that to the
Denominator.
denominator and you didn't do that? We didn't do that with the z negative 3.
I'm going to rewrite that one for just a second. Make it clear. That would be x to the negative 3 times 4. And when I take negative 3 times 4, I get a negative 12. And so because this is, because
the product was a negative number in the exponent
is a negative, we need to change it into a positive.
Okay, got it.
All right?
Yep.
Okay. What if instead I had numbers? What if I had 2 to the third to the second? In each of the ones above, the base stays the same. And so here we have to keep the base. And so that would give me 2 to the 3 times 2 is 6. And when I multiply out 2 to the 6th, and when I evaluate it with my calculator, I believe you get 64. And one more, if I have 10 to the second to the negative second. Again, I'm going to multiply those exponents, 2 times negative 2. And that product's going to give me negative 4. Now, should I leave that with a negative exponent? Or do you think maybe we ought to rewrite that one with a positive exponent?
Yes.
I'm thinking for now, let's make that positive. Negative exponent means I want to move that to the denominator. And that gives me 1 over. And what's interesting, let's see, 10 to the 4th is 1 over 10 with 4 zeros. So 1 over 10,000. And sometimes you might want to express that as a decimal. And when you divide that out with your calculator, you'll get 0.001. Is everybody all right with this idea, though, that when I raise a power to a power, I multiply those exponents?
Yes.
Great. Then the next that we're going to look at is a rule for raising a product to a power. And so let's look at an example. Let's look at if I have AB to the third power. And again, I want to work out this example so you can sort of see why the rules apply. AB to the third power, well, if I raise something to the third power, I multiply it by itself 3 times. It would be AB times AB times AB. And if I think of rearranging, wouldn't I have 3A's, A to the third, times 3B's, B to the third? And so in general, if I raise a product to a power, I raise each factor to that power. To raise a product to a power, we raise each factor to that power. When you do this, though, pay close attention to parentheses placements. Watch for parentheses. So let's say, for example, I have 2Z in parentheses being raised to a power. Because of the parentheses, the whole product is being raised to the power. So I need to raise 2 to the third, and I need to raise Z to the third. And now 2 to the third, 2 times 2 times 2 would give me 8 Z to the third. And when I say watch for parentheses, be very careful. Notice that that is very much different than if I just had 2Z to the third without the parentheses. Without the parentheses, only the Z is being raised to the third power. What if I have 6x to the fifth, and I'm raising that in parentheses to the second power? Because of the parentheses, the 6 would be raised to the second power, and the x to the fifth would be raised to the second power. 6 to the second is 36. And again, we just said when we raise a power to a power, we multiply those exponents. So that would give me 36x to the 10th. Another example, if I have 3x to the second y, all being raised to the fourth power with parentheses, each factor inside the parentheses gets raised to that power. So I have 3 to the fourth. I have x to the second to the fourth, and I have y to the fourth. 3 to the fourth if I take 3 times 3 times 3 times 3, I believe that gives me 81. With the x's, when I raise a power to a power, I multiply those exponents. So I'll have x to the 8th, and then I'll have y to the 4th. And one more. If I have negative 5 y to the 5th, and I'm raising that to the 2nd power, I'm taking each factor and raising it to that 2nd power. So I'll take negative 5 and raise it to the 2nd. Then I'll take y to the 5th and raise it to the 2nd. Be careful. Negative 5 means negative 5 times negative 5. And so that'll give me a positive 25. And then here with the y's, when I raise a power to a power, I multiply those exponents and get y to the 10th. How's that one look?
Good.
All right. Then next, we're going to look at what happens when we raise a quotient to a power. And so let's look at something like a over b squared, looking at an example. To square it means we're going to multiply it by itself. So we'll have a over b times a over b. And then when I multiply fractions, I multiply straight across. So multiplying the numerators, a times a is a squared. Multiplying the denominators, b times b is b squared. And so without that middle step, does it make sense that we can say that if I raise a fraction to a power, I raise both the numerator and the denominator to that power? So to raise a fraction to a power, you have to raise both the numerator and the denominator to that power. Or in general, if I have x over y to a power n, it'll be the numerator to that power, x to the n, over the denominator to that power, y to the n. So let's look at some examples. Do I need to wait for a minute, or are you guys ready for examples?
No, I'm good.
So let's say I have x over 2, and I'm raising it to, oh, let's say the 4th power. That's going to be the numerator to the 4th over the denominator to the 4th. And so that'll leave me with x to the 4th over 2 times 2 times 2 times 2 gives me 16. But they get a little bit more complicated than that. Let's say I have 6x to the 3rd over y, and I'm raising that whole thing to the 2nd power. I have to raise the numerator to the 2nd power and the denominator to the 2nd power. But now realize when I'm raising that numerator to the 2nd power, each factor gets raised to the second power. And so I end up with 36 x to the sixth over y to the second. Is that one all right? Next one's interesting. What if I have x over y and I'm taking that whole fraction to, let's say, the negative third power? I can take the numerator to the power over the denominator to the power. But then that leaves me with negative exponents. If I have a negative exponent of -3 in the denominator, it will become positive in the numerator. If I have an exponent of -3 in the numerator, it will become positive in the denominator. There's another approach that we can take to that one, because we said that when I raise something to a negative power, it means I take the reciprocal, I get 1 over that quantity to the positive power. The other approach that some people like to take is if I'm raising a fraction to the negative power, I'm going to raise the reciprocal to the positive power, and then raise the numerator to the power and the denominator to the power. Please notice that both take me to exactly the same place. Which is the better method? The one that makes more sense to you. One, we can just use that quotient to a power rule. And then remember that if I have a negative exponent in a fraction, I need to move that factor to make the exponent positive. Or we can look at it and say, hey, wait, I know my negative exponent means take the reciprocal to the positive power. And it gives me that same result. So let's look at a couple more examples. Making use of all of these rules. Let's look at 2x to the sixth, y to the second, all raised to the fifth, over negative 32 x to the 20th, y to the 10th. Order of operations tell us to work inside parentheses first. And in working inside parentheses, what I need to do, because there's invisible parentheses around the numerator and denominator, is first simplify the numerator and denominator first. So when I simplify that numerator, I'm raising that product to the fifth power. So that'll give me 2 to the fifth, x to the, let's see, 6 times 5 is 30. Y to the 2 times 5 is 10. There's really no work to be done in the denominator yet. In the numerator, 2 to the fifth is 32. We have that over that negative 32, x to the 20th, y to the 10th. Is everybody comfortable so far? Now, where you have to be careful is this is a negative number, negative 32. It's not a negative exponent, it's just a negative number. But if I divide 32 by negative 32, doesn't that quotient give me negative 1? Then with the x's, when I divide, I get x to the 30 minus 20 is 10. And then with the y's, when I divide, 10 minus 10 is 0. Well, y to the 0 just means 1, so I don't need to show that. And so my end result is just negative 1x to the 10th or negative x to the 10th. How's that one?
Okay.
Everybody okay? Next, let's look at something like x to the negative 10 over x to the negative 15. And this one, there's two approaches to it, depending on whether you see the glass as half empty or half full. What I think is easiest is to look at that as a division problem. And when I divide, I subtract exponents, the exponent of the numerator minus the exponent of the denominator. And remember that those double negatives make it a positive. And so that leaves me with x to the 5th. However, there's another approach that you can take. And I know that some students prefer this one because they find those negative exponents unnerving. What we could do is we could rewrite this with positive exponents before we begin. Negative in the numerator would become positive in the denominator. Negative in the denominator would be negative exponent, pardon me, and that denominator would become positive if I moved it to the numerator. And now when I subtract, I get that same result. So either is fine. It's just a matter of personal preference. So far, so good.
Yep.
If so, that's the end of the exponent laws. One place where they're frequently applied is with scientific notation. And when I look at scientific notation, in order to really be proficient with it, what we ought to start looking at are our powers of 10. And so if I take 10 to the third, 10 to the third, doing a little bit of scrapbook off to the side, is 10 times 10 times 10. Wouldn't that give me 1,000? If I have 10 to the second, 10 times 10 would be 100. If I have 10 to the first, well, that would just be 10. And please notice here that the power on 10 with these turns out to be the number of zeros in my answer. Then if I have 10 to the 0 power, well, anything to the 0 power is always equal to 1. If I keep going down, 10 to the negative 1, by definition, that's 1 over 10, and 1/10 as a decimal is 0.1. If I have 10 to the negative second, that would be 1 over 10 to the second, or 1 over 100, which would be 0.01. And if I have 10 to the negative third, that would be 1 over 10 to the third, which we just saw was 1,000. And that would take me to 0.001. And these powers of 10, I'm going to shrink this down just a little bit so I can write something below it. The powers of 10 correspond to our place values. Ah, the battery is going in my stylus. I'm sorry.
And what did you just say? The powers of 10 correspond to our what?
Place values.
Oh, thank you.
Can you hear me all right? Do you need for me to use the headset?
No, but it's good. I just missed it.
All right, so if I look at a decimal number, that first digit to the left of the decimal is the ones, which would be my 10 to the 0. That next digit would be the tens, which is my 10 to the first. The next digit would be the hundredths, which is 10 to the second. The next digit would be the thousands, which is 10 to the third. And if I work backwards, the first one to the right of the decimal point will be the tenths, which is 10 to the negative first. The next one is the hundredth place, which would be 10 to the negative second. And the next one after that would be my thousandths, which would be 10 to the negative third. And so we say we work in a base 10 number system. We call it a decimal number system because that prefix deci means 10. And it's because our place values are all powers of 10. And also we have 10 digits, the digits 0 through 9. Now, when I look at a number in scientific notation, we say that a number is, in scientific notation, if it's written in the form A times 10 to the n, where A has to be a number bigger than 0, but less than, I'm sorry, I wrote that wrong. I apologize. A has to be greater than or equal to 1, but strictly less than 10. And n is an integer. And so what you have to realize is if A is bigger than 1, but less than 10, there's only one digit in front of the decimal point. And so let's start by looking at some numbers that are in scientific notation, and we want to instead express in standard notation. So let's say I have 4.37 times 10 to the third. Well, one way you can do that is look at the fact that that means 4.37 times 10 to the third is 1,000. And if you multiply that out, you get 4,370. But that's the hard way. Instead, if I look at 4.37 times 10 to the third, the exponent on 10 tells me how many places to move the decimal. And so if I have 4.37 times 10 to the third, it means I'm going to move that decimal point 3 places. And over here where there's an empty space, we'll fill in with a 0. And so that would give my 4,370. And so, for example, if I have something like 6.97 times 10 to the fifth, I'm going to take that 6.97. I'm going to think of moving my decimal place 5.5 places, 1, 2, 3, 4, 5. So my decimal point would be here. And I have to fill in with 3 zeros. So that gives me 697,000 or 697,000. And please notice, if the exponent on 10 is positive, you get a larger number. And so I move my decimal point in a direction that makes it larger. Instead, if I have 7.34 times 10 to the negative third, well, that would be, if I worked it out, 7.34 times 1,000. And when I multiply that, I get 0.00734. But it's easier instead to say that that tells me how many places to move the decimal point. But because it's negative, we're going to move in the other direction. We're going to get a smaller answer than the original number. So I like to think that if my power of 10 is positive, I'm going to get a larger number. If my power 10 is negative, I'm going to get a smaller number. I know some people have learned if the power of 10 is positive, I'm going to move to the right. If the power of 10 is negative, I'm going to move to the left. But now I'm going to confess something to you guys. I'm one of those people that no matter how old I get or how many degrees I get, I still confuse my left and right from time to time. And so to tell me, move it to the right, move it to the left. It's like a crap shot. It's a 50-50 shot whether I get my directions correctly, as opposed to saying, okay, positive is bigger. I'm going to move it to make a bigger number. Negative is smaller. I'll move it to make a smaller number. Somehow that sticks better with me than left and right. How about you guys? Do any of you ever get your directions mixed up from time to time?
Yeah.
Yes.
So I've got that 7.34 times 10 to the negative 3. I'm going to take that 7.34 and I'm going to move the decimal in the direction that gives me a smaller number. Fill in zeros for the missing places, and I get that 0.00734. So if you're given a number in scientific notation, let's look at one more. Let's look at, I have no idea why my phone is ringing off the hook right now. Sorry, folks. Let's look at 1.23 times 10 to the negative 5th. Got that 1.23. I want to move the decimal point in the direction that gives me a smaller number, 5 places, 1, 2, 3, 4, 5. In order to do that, I'll have to fill in 4 zeros, and that gives me 0.0000123. Please realize that the exponent doesn't necessarily tell me how many zeros I need, but the exponent tells me how many places to move that decimal point. Can we try some more? Actually, rather than trying more of these, let's look at if you express a number in scientific notation. So let's say, for example, I have a number like, whoops, sorry about that, 95,800,000. And I want to put it in scientific notation. Again, first of all, I look at this, and does everybody see that this is a large number? So the exponent will be positive. And again, I want to have only one digit in front of the decimal. So I want to move the digit so that it's behind the 9, in between the 9 and the 5. That gives me 9.58 times 10. And now we're going to have a positive exponent. Originally, the decimal is at the end of the number. So I'm moving it 1, 2, 3, 4, 5, 6, 7 places. So that gives me 9.5 times 10 to the 7. And the exponent is the number of places you moved that decimal. So another example, let's say I have 245.7, and I want to put it in scientific notation. write it down here, 245.7. Is everybody all right? That number is over 1. So we're going to have a positive exponent. I want 1 digit in front. So that gives me 2.457. Now to find the exponent on 10, when I move the decimal from here to here, I'm moving over 2 places. Instead, if I have 0.000123, is everybody all right looking at this case? This is a smaller than 1 number. So I'm going to have a negative exponent. I'm going to rewrite it for just a minute. I want 1 digit in front of the decimal. So that gives me 1.23 times 10 to, again, because it's a small decimal number, we're going to have a negative exponent. And when I go from here to here, I'm moving it 1, 2, 3, 4 places. How's that look? And so some people wonder, why scientific notation? And so let's use scientific notation to simplify. And I'm going to have 3,200,000 divided by 0.12345 And now I'm guessing that most people would pull out a calculator to do something like this. But even using a calculator, sometimes I start going cross-eyed, typing all those zeros in. And back in ancient times, when we had to do division like this by hand, it was tough keeping all of that straight. So instead, I'm going to think of these numbers in scientific notation. The first would be 3.2 times 10 to the 1, 2, 3, 4, 5, 6. The second would be 1.6 times 10 to, this is a tiny decimal, we'll have a negative exponent, 1, 2, 3, 4, 5, 6. Now I'm going to think of writing that as a fraction. And 3.2 divided by 1.6 is a straightforward division. That would give me 2. I'm sorry, I miswrote this. I'm sorry, that was a 6, not a 2. And here on the tens, because I'm dividing, I'll subtract the exponents. So that gives me 2 times 10 to the 12. The decimal point is here. So when I move 12 places, what is that? Hundreds, thousands, millions, billions, 2 trillion. And sometimes putting those numbers in scientific notation is almost easier than trying to type all of those zeros into your calculator. How is this idea of scientific notation? Is this something that you've seen before? Stop sharing for a minute and try to look. Oh, I don't see anybody's faces to judge a reaction anyways. Any reactions? How's this going? Is this all right? Any questions?
Going pretty well.
Good. If it's going all right, then we're going to just change gears a little bit because we've been focusing on exponents. But the reason that we're focusing on exponents is because we need them to help us look at polynomials. And when we look at polynomials, today we're going to start by looking at a lot of definitions. And the first is that of a term. And in math, when we talk about a term, we talk about a product of constants and variables. And so if I look at that word product, I think we've already discussed that that word product tells me that I'm multiplying. And I think we've already said that for the most part, our constants are numbers. And usually our variables are letters. I think we already defined the idea of the coefficient. And the coefficient on a term is the constant factor. The number factor, the number that's being multiplied, usually in front. And when we talk about the degree of a term, we're referring to the sum of the exponents on the variables. And so in that homework, which, let's see, is homework number 21, you'll see things like 3x to the fourth. And as that is written, that's 3 times x to the fourth. The constant is 3. The variable is x. When I look at this, the coefficient is the constant factor, or 3. And the degree, well, there's only one variable with an exponent, so it would be that exponent 4. So we'll say it's 4th degree. If I have 6y, what would you tell me the coefficient is? Anybody?
6.
Beautiful. And what would the degree be? When I look at that y, what is the exponent on it? If there's no exponent written, doesn't it mean we only have one of them? And so that would be first degree. If I have x to the 7th, what's the coefficient? What's that number in front of the x that I'm multiplying it by? Ah! If there's none written, it's 1. So the coefficient would be 1. And the degree, the exponent on the variable is 7. So we'd say that's 7th degree. Next one's a little bit dicier. What if I have negative 12 x to the 2nd y? What's the coefficient? What's the number that I'm multiplying my variables by? Number out front is negative 12. But now over here, when I look for the degree, I've got 2 variables. And when I have more than one variable, I have to add those exponents. And so that would give me that this is 3rd degree. Because again, that y has an invisible exponent of 1. With me so far?
Yep.
If that's all right, then I'm going to change the page and look at a polynomial. We're going to define a polynomial as the sum of many terms. And when we look at the sum of many terms, we actually classify them by how many terms or the number of terms. The first that we look at is a monomial. And is anybody familiar with that prefix mono? Mono means beautiful one. So we have one term. So an example of a monomial could be something like 13x squared y, a single term. It could be something like just plain old x, a single variable. Or it could be something like 2. And if there is no variable attached, we can also call that a constant term, which has no variable. But those are all monomials. Next is a binomial. And bi means two. So a binomial will have 2 terms. So some examples of binomials might be something like 3x squared plus x. Might be something like 2xy minus 5y. Might be something like x plus 3. I have 2 terms that are being added or subtracting. Next is a trinomial. And that prefix tri means 3. So a trinomial will have 3 terms. And so examples might be something like x squared plus 2x plus 1. Might be something like 4x squared plus 6 minus x cubed. Anything that has 3 separate terms being added or subtracted. Once we get above 3 terms, we just call them a polynomial term. Polynomial, which again means that it has many terms. And so an example might be something like 6x to the 5th plus 10x to the 3rd minus 9x to the 7th plus x to the 2nd plus 2. And with a polynomial like this, there are several questions that could be asked. One question might be, what's the constant term? And remembering that a constant is just a fancy name for usually a number, the constant term would be the number that stands alone, or 2. Another thing that you might be asked to do is to put it in descending order. And in descending order, the exponents go down as you read from left to right. And so to put that in descending order, I ask, what's the highest exponent? That's 7. So I'd start with the negative 9x to the 7th. My next highest exponent is 5. So then I'd have 6x to the 5th. The next highest exponent is 3. So I'd have 10x to the 3rd. Then I'd have my x squared. And finally, the constant term will be last. When it's in descending order, we're asked for the leading coefficient. And the leading coefficient is the coefficient on the first term when it's in descending order. We can also look at it as a coefficient on the highest degree term. And so in this example, the leading coefficient is the negative 9. Again, the leading coefficient, once it's in order, is the first coefficient, the one where it starts. Then, after that, we sometimes ask for the degree of the polynomial. And the degree of the polynomial is the degree of the highest degree term and so when I look at that, negative 9x to the 7th plus 6x to the 5th plus 10x to the 3rd plus x squared plus 2, we would say that this is 7th degree, this is 5th degree, this is 3rd degree, this is 2nd degree. So the highest is 7. So we'd say that this is a 7th degree polynomial. And sometimes, I think there might be one question in the homework that asks you to fill in for missing terms. And so what happens is we use a coefficient of 0. So what does that mean? Here we have negative 9x to the 7th. Next, we have 6x to the 5th. You notice there's no x to the 6th term in the middle. So I'm going to add 0x to the 6th. Then our next term is 10x to the 3rd. There is no x to the 4th, so I can fill in 0x to the 4th. X to the 3rd is followed by x to the 2nd. There's no x to the 1st, so I'll put in 0x and then put the 2 at the end. And so when you're asked to fill in for missing terms, you're just putting those zeros in for powers that are not in your polynomial. So let's try another. This time, let's say I have 2y to the 4th minus y to the 5th plus 7y squared minus 10. And I want you to please put it in descending order. I want you to tell me what the constant term is. I want you to tell me what the leading coefficient is. I want you to tell me what the degree of the polynomial is. And then I want you to fill in for missing terms. And I'm going to stop for a minute and be quiet and have you folks do those. And so what are you folks getting? In descending order, are you getting negative y to the fifth plus 2y to the fourth plus 7y to the second minus 10? So far, so good.
Yes.
Then constant term, the plain old number, is negative 10. Leading coefficient, now that they're in order, the coefficient on the first term is negative 1 degree. The highest degree term, the highest exponent is 5. So this is 5th degree. And then to fill in for missing, well, I have negative y to the 5th. Next exponent going down would be y to the 4th. Next going down would be y to the 3rd, but there is none. So I'll fill in a 0 y to the 3rd. Then I'd have y to the 2nd. There is no y to the 1st or plain old y. So I'll have 0 y and then that minus 10. So far, so good.
Yep.
If so, then the next thing you might be asked to do is evaluate a polynomial. And what we're going to do is we're going to substitute a value for the variable. And simplify. But we have to remember the order of operations. So what does that look like? Let's say, for example, I ask you to evaluate 5x squared minus 4x plus 7 when x equals negative 2. So what I need to do here is substitute in negative 2 for x. Thinking about what we did last unit, this could also be written if f of x equals 5x squared minus 4x plus 7. We could be asked to find f of negative 2. Both tell me to do the same thing. Both tell me to replace x with negative 2. And so where I had 5x squared, in place of x, I'll put a negative 2, minus 4x. In place of x, I'll put a negative 2, plus 7. Especially those of you who are using a calculator to do this, it's important to put parentheses around, especially if you're substituting in a negative number. I think we've discussed that already. So now order of operations, first is parentheses. There's no work to do inside. Next is exponents. Negative 2 to the 2nd would be 4. After exponents, we multiply and divide as they come from left to right. And final answer we add to get 35. We've done some of that type of problem already. Let's just try another. Let's say we want to evaluate. This time, let's say I have negative 6y plus 5x when y equals 3 and x equals 2. And again, I think when we were looking at those linear functions and graphing lines, we did some of this substituting for two variables. Where there's a y, I'll put a 3, so that becomes 6 times 3, plus where's an x, I'll put a 2, 5 times 2. Order of operations, no work inside the parentheses, no exponents. So first I'll multiply, negative 18 plus 5 times 2 is 10. And then when I add, I get negative 8. So far, so good.
Yeah.
And so that's the type of work you'll see in that homework 21 that asks you to evaluate asks you just about polynomial definitions. You might also see something that refers to like terms. And I think we've spoken a little bit about like terms in terms of simplifying expressions. Like terms have the same variables with the same exponents. And so, for example, if I have 4x and 3x, they both have the x with an exponent of 1, so those are like. If I have 4x and 3x squared, they both have x's. But do you notice the first one is x to the first and the second one is x to the second? So because the exponents are different, they're not like. Let's say instead I have 4x squared and 3y squared. And now these two both have the same exponent, but they have different variables. So they would not be like. If I have 11x squared y to the third and x squared y to the third, they both have x's, they both have y's. On each of them, the x has an exponent of 2. On each of them, the y has an exponent of 3. So the variable parts are identical. So those would be like terms. And one more. What if I have x to the second, y to the third, z, and x to the third, y to the second, z? Are those like? Well, they each have an x, a y, and a z.
No, right?
Right, this one's they're not like because the same variables do not have the same exponents. If I just look at the x's, x to the second and x to the third, they're different. And so when we look at these polynomials, the reason that we need to know whether we have like terms is because we can simplify by combining like terms. And when I combine like terms, what we do is on like terms, we can add or subtract, depending on the operation that's given, the coefficients. The variable parts remain the same. And in some ways, what we're really doing is we're using the distributive property backwards. So what do I mean by that, using the distributive property backwards? If I have 2x plus 6x, those are like terms. So it's addition, I'll add the coefficients, 2 plus 6, and keep the variable part x. And you notice how usually with the distributive property, you start with this and you distribute to each of them. And then 2 plus 6 is 8x. Instead, if I have 5y minus 9y, they're like terms. So I'll this time subtract the coefficients because it's a subtraction problem, keep the variable part the same, and get negative 4y. Instead, if I have 3x squared plus 2x plus 4x squared. Now here, they're not all like terms, but some are. In my mind, I can picture rearranging using that commutative property of addition to change the order. And then I can combine my like terms, getting 7x squared plus 2x. But that last one, because it's not like, I cannot combine it. And so that would be my final answer. And let's look at one more before we call it a day. Let's look at 6z plus 5 minus z plus 2. And does everybody see with this example, I have some like terms. My z's are the same, 6z minus z, and my constants are the same, plus 5 plus 2. 5 plus 2 will give me 7. And does everybody remember this plain old z? I can think of there being an invisible 1 there. And so 6 minus 1 will give me 5z plus 7. How's it look so far?
Okay.
Okay. Now I'm going to backtrack for a minute. And over here, I'm going to scroll up to the top. And because I had thought we had gotten further, I remembered us getting further with the exponent rules. I did not change the assignment. I will change that assignment before I move it, anybody who's got a perfect score on it, I will give you extra credit. So that assignment 19 will be due on the 22nd, and we didn't get quite far enough, so don't worry about 22. 22 will be due on the next class, which I believe will be the 22nd. All right. And I apologize that I didn't do that right away after the last time we met. And before we call it a day, let me stop sharing. Let me stop recording.